work on multi-loop circuits. So we have a couple of rules. We've already seen the rules already, but we're going to sort of frame them a little bit differently. One's called the junction rule. It just says that the currents going in to a junction equal the currents going out. We already saw that, right? We saw that with resistors in parallel, that the ingoing current is equal to the outgoing current. And then the other is going to be the loop rule, which says that if you go around a closed loop in any circuit, not even the entire circuit, but just a closed loop within a circuit, that the sum of the potentials in that loop is equal to 0. We've seen that with resistors in series, that the voltage of the battery equals the sum of the voltages across the resistors. And so we've already seen these two rules, but we're just going to frame them a little bit differently, and we'll see some additional guidelines for these rules. So first is Kirchhoff's rule. It says that the sum of the currents entering a junction must equal the sum leaving the junction. Give me just a second. Did this happen in here the other day where my pen didn't work, or was that another class? Was that here? Okay, I got it. So the sum of the currents entering a junction. I fixed it. Lana, you need to tell us when we're being goofy. Yeah. Right. I've sat in class before, and I'm taking classes, right? And I sat in class, and the professor's up there messing around with a computer. It's like, I know what the issue is, but he doesn't ask me, so I don't feel like I can usurp his authority and just go up there and fix it for him. Let's equal the sum leaving the junction. And so if I have a current going in, that must equal, I'll call this I1, I2, must equal the currents leaving that junction. I equals I1 plus I2. So for example, if I have 8 amps going in and I have 5 amps here, then I must have 3 amps there. It's necessary for me to have 3 amps there. Otherwise, I have current going somewhere that it's not supposed to be going. You can also have multiple junctions. You can have as many junctions as you want, where I can have, say, 2 amps, 4 amps, 6 amps, 7 amps, and 3 amps. And if I want to know what is the current leaving out here, well, I would say 2 plus 6 plus 7 equals, that equals 8 plus 7 is 15. That's the ingoing currents, right? 2, 6, 7. Outgoing currents are 3 plus 4. That's equal to 7. So I know that this current has to be outgoing, and it has to have a value equal to 8 amps. All right, so that's the junction rule that is based on the conservation of charge, that if I have charge going into a junction, I have to have that charge coming out of the junction. The loop rule is that the sum of the potential differences that's, delta V, across all the elements around any closed loop must be 0. We've already seen this. We said that the sum of the voltages across this loop, for example, are equal to V minus V1 minus V2 equals to 0. We said that when we go across resistors, when electrons go across resistors, they lose energy. Like the roller coaster, not the chain going up, but when you come down the hill, your roller coaster car loses potential energy. And so in a similar way, our electrons lose energy when they go across these resistors. The great thing about the loop rule is, look, you can have a very complicated circuit with lots of different things going on. Resistors here, batteries, resistor. You can just have this mini looped circuit, and I can take any single loop within there. Like, for example, I could take this loop and say the sum of the voltages equal to 0. Or I can take this loop and say the sum of the voltages equal to 0. So I don't have to consider the entire circuit. I can just take one small part of the circuit and say the sum of the voltages around this particular closed loop, they have to equal to 0. Because anytime I have an electron, it has a certain amount of energy at this point. It travels through this circuit. It has to have the same amount of energy at that point. Okay, so the loop rule is based on the conservation of energy. Let me write this. So based on conservation of energy, whereas the junction rule is based on which law of conservation? You'll recall I said it, but I didn't write it down. Y'all remember? It's the conservation of charge. I can't lose charges. Just wherever. All right, so those are our loop rule and junction rule. We'll have a couple of guidelines for the junction rule, and so let's go over those. These will seem like rules, but they're not really rules. They're just sort of guidelines. No, they're rules that you have to follow. All right, so when we get to multi-loop circuits, as we'll do this morning, we're going to have two directions that we're concerned about. One is the direction of the current. We're going to pick the direction of the current. And then the other is the direction that we travel through the circuit. So we're going to start at a point in the circuit, and we're going to go around the loop, adding up the potentials, and we need to know the direction of the current, which you're going to select. Doesn't really matter what you select. And then you also select the direction that you travel through the circuit. Doesn't matter which direction for either of those that you pick. But it does affect the values that you'll get. So let's imagine in each of these cases that you're traveling from point A to point B. So I'm going from here to here. I'm going in that direction. Now let's imagine for these that I have a current, in this case, that's going in the same direction. In that case, delta V across that resistor is equal to negative I times R. This is sort of the normal way that resistors operate. That if I travel in the direction of the current, resistors see a drop in energy per charge, or a drop in potential. That's normal for resistors. But let's say that you go the opposite direction of the current. So instead of the current going left to right from A to B, let's say that the current now is going in this direction, but you're still traveling in this direction. So here, I say traveling, you're going through the circuit opposite the direction of the current. In that case, delta V is not normal. That's not the normal thing that you go against the current. And so it's going to do the opposite of what it did before. So when I go across a resistor against the direction of the current, I imagine that my charges feel an increase in potential. Now this isn't real, right? Electrons don't do this when they're traveling through a circuit, but we're just imagining that that's the case. Mathematically, it'll help us to work through this loop rule. And then for batteries, if I go from A to B still, let's say I do right here, I'm going from this to this direction, so I'm traveling in this direction. In this case, it doesn't matter the direction of the current. Is irrelevant. All right, so in that case, the battery does what it's supposed to do. And is the battery supposed to increase the energy of the charges or decrease the energy of the charges? It goes up, right? It's like the chain on the roller coaster. Sugar, 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 sugar. Right? It increases the energy of the roller coaster car. It increases the energy of the electrons. All right. So in this case, my change in potential is delta V equals positive E. Now, what if this is going from? This is going from low to high potential. Sorry, I might have said that incorrect. Oh, shoot, I'm sorry, I should have said this. When I'm going from low to high potential in this way, I'm going from where my electrons have little energy to where they have a lot of energy. All right? So I always like to think of this as the roller coaster. There's my roller coaster car, and it moves up and they gain energy. Because I'm moving from low to high potential. Sorry, I might have misspoke earlier. I don't really remember what I said a minute ago. But is this clear that if I'm moving in the direction going from the little side to the big side, from low to high potential, that my charges gain energy? You remember that? Like get across okay? All right. So here, I'm going in the opposite, or I'm going in the same direction, but notice that the sides of the battery are switched. So now I'm moving from high potential to low potential. High to low, and in that case my change in potential is equal to negative of the EMF. That E is just, the EMF of the battery. That is the voltage of the battery without the internal resistance, so sort of this pure voltage, just the energy and not the resistance. I like to think of this as like sliding down a slide. That when you come to this, your electrons or your charges, they actually start up here and they go down and they lose potential energy. They go wee. They go down the slide. All right, so they lose energy. When I was a kid, my mom, she kept children like in her home. Right? I mean, now you have to have a license and all that, but she didn't have any of that. But she kept children in her home, and she used to take us all to the park. Right? She had about 20 kids, maybe 15 kids that she kept. And she would take us to the park, and we'd play, and we'd have a good time and all that. But she is, this is 30 years ago, 40 years ago. And the parks, we had those metal slides. We don't have those anymore. And some of the old parks do, but they usually don't. The metal slides, you ever been on one of those? They're fun, they're fast, they're usually really tall. And they get hot, right? Yeah. But we had a girl, she was probably, and she went down the metal slide. No shoes on, right? Why would you wear your shoes at the park? You take them all off when you get there. And she was going down the slide. And you know how the slide, they have that little thing that comes over the lip, that comes over the side? Well, at this part, the slide was, damaged, if you will. And these little things didn't come over all the way, because part of it got fried away. You know what happened to her? No, she didn't cut her leg. Sorry, it's a little gross. It tore her little toe off. Like it caught it and ripped it right off. Yeah. Yeah. So she has 4 toes now. But unfortunately, it was a friend of my mom's, so she didn't get sued or anything. But the point of that is that when you go down the slide, moving from high to low, you lose your toes. Or you lose energy, you lose energy. Does that help you at all? Not really at all, does it? But if you move from high to low, you lose your toes, or you lose your toe. Or you lose energy, really is what you lose. Huh? Yeah, that's a real story.
Your mom just picked up kids?
Yeah, they paid her to keep them. She didn't go out and kidnap the kids, no. It was she ran a daycare. But that's sort of beside the point. The point is that when you go down the slide, from high to low, you lose your toe. Or you lose energy, really is what you're losing. You lose something. Yeah. Really?
She was riding on the handlebars of her bike and it got caught in the spokes and it just sliced the little toe.
Yeah, you don't really need the little toe, it's not that.
You should wear shoes. That's
You should wear shoes, right? Okay, so for resistors, when you're traveling with the current, the change in potential is negative. That's sort of what resistors do. If you're traveling against the current, the change in potential is positive. My aunt cut off my uncle's toe when they were kids with a hatchet. Because he said, Cherry, that was her name, Cherry, I bet you won't cut off my toe. She said, I bet I will. What? Okay, so for batteries, when you have electrons traveling from low to high, that is, from the little side to the big side, in that direction, the change in the potential is positive. The charges have gained energy. I say electrons, but really we think about protons, right? That when they move from low to high, the protons have gained energy. And we can think about, the mountain. If I have a proton that moves in this direction, from low to high, it has gained energy. When you have electrons traveling from high to low, potential, that is, from the big side to the little side, from high to low, what do they lose? They lose their total, our energy. The change in potential is negative. And this isn't the normal way for batteries because the electrons don't gain energy, they have lost energy. So delta V is negative. Here, delta V is positive. Now, why would you want to cause electrons to flow from high to low potential? Why would you want to have electrons go from this side to this side of a battery? What purpose could that possibly serve? Because the electrons are actually losing energy. Why would you want your electrons to lose energy when they go into this battery? No, that's a good guess. Can you think of any, you do this every day, I know all of you do. Can you think of any reason why we send current the opposite direction to a battery the way it's intended? To charge your phone, right. So that's what you do. Those electrons go in the opposite direction, they lose energy, and that energy in your rechargeable batteries, it's not for all batteries, but they are converted back into some sort of chemical energy in the battery. All right, so like, for example, rechargeable batteries. Is there an E? I don't think so. All right, let's try this. What is the current in this circuit? You're going to need to use the loop rule. You'll need to just pick a direction for the current. Doesn't matter what direction you pick for the current. It can be clockwise or counterclockwise. And then you pick a direction to travel through the circuit, applying the loop rule as you do so. Adding up the potentials of all the individual things, all the resistors and batteries. Oh, man. Y'all work on that. I'll figure this out. You're going to pick a direction for the current. Doesn't matter what direction you pick. Just pick one, clockwise or counterclockwise. It doesn't matter. And then pick a direction to travel through the circuit. Start at a point, go through each element, and then ask yourself, is this a positive or a negative change in potential? Add all those up, set them equal to 0, and then you can solve for the current. looks like y'all are having a little trouble on this. Let me give you a little kickstart. Let's say that I say that my current, I'm just going to pick a direction. I don't really know what the direction of the current is, but I'm going to say that it's in this direction. I just picked it. It doesn't really matter. But I'm saying that the current is in that direction. And now I'm going to start at this point. Doesn't really matter where I start or which direction I go, but I'm going to start at this point, and I don't know, just to be honorary, let's go this direction, opposite the current. Okay? So now I've picked my two directions. And now I want to go through and figure out what is the change in potential for each. So starting here, I know that the change in potential is 6.6 I, but then is it positive or negative? Well, am I going with or against the current? I'm going against. And if I go against the current, it's what? Positive or negative? It's positive, so it's plus 6.6 I. And then I come up here, let's see, this isn't a slide, this is like the chugga chugga. So is that plus or minus 18? Is it plus or minus 18? It is plus, because I'm going from low to high. And then you go through and you do the rest. You do the 2, you do the 12, you do the 1. Add all those things up, and then set them equal to 0. That's our loop rule. And then you solve for I. All right. Good fraction of you have the right answer. Let's stop in about 15 seconds at 5:10. Ask your neighbor what they put. Compare your answers. Guess if you're not sure. I'm going to stop in 5 seconds. 5 seconds. Once you do these a few times, you'll say, those are easy. But right now, it's sort of funny right now to see A is the right answer. So I go through. I've gotten up to this point. Then I say plus 2I, because I'm going against the current. When I go against the current, I have a positive change in potential. Here, it's like I'm going down the slide. And when you move from high to low, you lose energy. So I have minus 12. And then I have plus 1I, because I'm going against the current here, and I come back to the point where I started, so I say all that's equal to 0. And so I get 6.6 plus 2 plus 1, that's 9.6I, plus 18 minus 12, plus 6 equals to 0. And so I is equal to minus 6 divided by 9.6, which is equal to 0.63, negative 0.63. Now, the meaning of this negative right here, it wasn't important for the answer because you just wanted to know the magnitude of the current, not the direction. But this negative says you chose the direction of the current incorrectly. And so when you're working through these and you find that you get a negative I, I'm going to ask you for the direction of the current. And here you would say, well, gosh, I is not counterclockwise. You would say that I is clockwise, which is opposite what you chose. So you see, it doesn't matter the direction of the current that you choose, because if you choose the wrong direction, then it'll come out in the end as a negative value. We'll see that later when we actually work multi-loop circuits. Now you're not going to see a problem like this on the test. You're going to see multiple loops in your circuit, but it'll be similar. It'll work out in a similar way to this. Let's do one of those, a multi-loop circuit. All right, so you'll have a question like this. You'll have several questions that look like this, but you'll have one that's just a circuit with some numbers on it, and I'm going to ask you to tell me what are the currents in each of the loops of the circuit. So first of all, how many loops do you think this circuit has? How many distinct loops does this circuit have? Does it have one loop? Does it have two loops? Right. Does it have three loops? Yeah. Four? It has three. It does have three distinct loops. Let me show you. So you have the left loop, the right loop, and the big loop. You got this loop. You got this loop. That's a closed loop. And then you also have this loop. So we have three distinct loops. So we can write the loop rule for three of those loops. We can also write the junction rule. How many junctions do we have in this circuit? 1, 2, 3. How many junctions we have? We just have two junctions. We have this junction and this junction. So you'll be able to write a total of 3 equations for the loop rule. And you can sort of write 5 equations, though the two junction rules are really just flipped, right? So they're basically the same, because you have like in equals I out, and then on the bottom you have I out equals I in. So we really just have 4 equations. So we have 4 distinct and independent equations, and with a system of 4 equations, you can solve for 4 unknowns. Now, unfortunately, we only have 3 unknowns. We just have our 3 currents. And so you'll have to, on the test, take a system of 3 equations and solve for 3 unknowns. Mathematically, that's just a handy skill to have. And many of you know how to do that. We've done it before in this class. But it's a skill that you can take forward into your other classes if you haven't really mastered that yet. Okay? Just,
Do the batteries play no part in the loops?
the batteries do play a part, yeah.
So do you originate at the battery?
Doesn't matter where you start. Yeah, so when we talk about traveling through the circuit or starting at a particular point, there's no physical meaning behind any of that. It's just a convention that you choose. So let's write the equations for this one. Let's do the left loop first. This darn screen is not working. What's wrong with it? Somebody help me. Oh, I have the eraser on. Thank you. I fixed it. As y'all are so helpful to your faculty. We really appreciate you. Okay, I'm going to start here. Notice that I've already chosen the directions of the current. Well, let me point out that too. Notice that we have 3 distinct currents here too. I have I1. That's I1. I have I2. That's I2. And then I also have I3. Notice I have 3 distinct currents. And also notice that the currents begin and end when they come to the junction. Because your current will always change when you go into a new junction. Because you got other currents coming and going out of that junction. It will change your current. Almost always. It is possible to have 0 current in a multi-loop circuit. Like it is possible to set it up so that this current actually is 0. And if you look back at some of the old tests, there was actually a test question where that happened. So don't freak out if you see that. But let's look at the left loop first. I'm going to start right here. And I'm going to move in this direction. So I got plus V1 because I'm going from low to high. And then I come to the resistor and I ask myself, am I going with or against the current? I'm going with. So it's minus I1R1. And then I'm going to do the left loop, so I come up. Is that plus or minus V2? Don't answer, just think. Is it plus or minus V2 when I'm moving up in this direction from this big side to the little side? Is it plus or minus? It's minus, right. So I have minus V2. And again, don't answer, just think. Is this plus or minus IR when I'm moving across this resistor? Well, the relevant thing that you want to ask yourself is, what is the direction of the current, and how am I moving relative to it? Am I going with the current or against the current with this resistor? I'm going against the current. And remember, that's sort of not the normal thing with resistors. And when not the normal thing happens with the resistors, I don't get a drop in potential, I get an increase in potential. So I'm going to have plus IR. But listen, this is where students mess up. You got to be very careful that you get your subscripts right. My R is R2. So I write an R2 right here. And my I is I1, right? No, it's not I1. I'm sorry. I was trying to trick you. It's actually I2. And that's equal to 0. Okay? So be careful. Often students will put I1 here because, Dustin, they say exactly what you said, is that, oh, I'm doing a left loop, and they sort of get used to writing I1, I1, I1. But then they come up here and they don't recognize that we have a new current here. So you have to use your new current. Okay? So this should be I2. Let me write that so it's more clear. All right. Now let's look at the right loop. I'm just going to pick a point. Let's just start right here, and we'll go in this direction. I have minus V3. In fact, y'all just take a moment and go through and write their loop rule, and then I'll write it for you in just a couple minutes. I'll give you about 1 minute to work that. Just write out the loop rule for the right loop. Make sure you get your subscripts right. Make sure you get your signs right. Subscripts and signs. Yeah, Brandon.
Where is the direction change? This.
All right. So I have minus V3. I have I3 R3 plus or minus for that. It's plus because I'm going against the current. Then I'm come back down here and notice that I'm coming into I2 territory. So I get I2 R2 plus or minus. That's minus. I'm going with the current. And then I get V2 plus or minus is plus. It does what batteries are supposed to do when you go from low to high. And so that's equal to 0. Now I can write the big loop too. You don't really need to, I'll show you, but let's go ahead and write the big loop. The outer loop, we'll just start, say right here, and move in that direction. I'll get plus V1 minus I1 R1 minus V3, because I'm going from big to little, from high to low. When you move from high to low, you lose energy. Plus I3 R3. Positive because I'm going against the current, and the resistor does what it's not really meant to do. And then that's it. I set that all equal to 0. Like I said, I can get 4 equations actually, right? And when you work these, you want to pick 2 of these equations to write. And we'll see that sometimes there might be some equations that are easier to solve than others. But then we can also look at the loop, or the junction rule. I can look at any junction in our circuits. We'll only have 2 loop circuits, so we'll just have 2 junctions. But if you have 3 loop circuits, you have more than that. Or if you have 5 loops or 6 loops, you have a lot more. You have a lot more junctions. But here I ask myself, what are the incoming currents? What are the incoming currents for this junction? Well, I1 is one, right? It's coming in right here. Is there another current that's incoming? I2 is coming in. What about I3? Yeah, so in this case, actually, the way I've chosen the directions for the currents, I1, I2, and I3 are all incoming currents. Now, that's not really physical, right? I mean, it is possible. There's really only one scenario where this could be physical, And that is if there's no current at all in the circuit. And that is possible. You can set up batteries opposing one another and have a circuit where you have no current flowing in it. I mean, that doesn't really do anything for you, but you can do it. But what this means is that likely I've chosen the direction of the current incorrectly. And so one or more of these are going to come out negative. Okay, so the numbers will all work out in the end. All right, let's at least start on this example on the next page. Here, I want to know the current through each of these resistors. And this is more like what you'll have on your test. I'll just give you a circuit. It'll have some resistors and some batteries. And I'll ask you to solve for the current in each of the resistors. Just to give us some consistency, I'm going to label the currents for us. But, I don't have any ideas about the direction of the current that I want. But just so we're sort of on the same page, and then I'll let you go. Not let you go, but let you work this problem on your own. I'm going to take I1 to be right here. So remember, I1 starts here, goes through this part of the circuit, the upper part of the circuit. I'm going to say that I2 moves through that middle branch, and then I'm going to say that I3 goes through this branch. Okay, so now you have numbers for the resistors. You can write out your big loop, top loop, bottom loop, and you'll also want to know the junction rule. All four of those equations. Actually, you only need 3 equations, but I'm going to write all 4. So go ahead and take a couple minutes and write out the equations for the top loop, the bottom loop, and the big loop. Brennan?
How can I tell where they started?
Doesn't matter where you start. You can choose at any point. So, like, you can just start right here, or you can start right here, or you can start here. It doesn't matter. Doesn't matter your directions. Doesn't matter where you start. Doesn't matter the direction that you travel through the circuit. All right, so these are the equations I'm going to do. Let's see here. I'm going to start. Oh, actually, you know what, guys? I have different numbers in my notes. Can I change them? Is that going to upset you? Oh, this is a completely different circuit in my notes. Oh, for crying out loud. Well, we'll just do it on the fly. So I'll start up here, and I'll do the upper loop. I have 14 minus 4I1 plus 10 minus 6I2. That's all equal to 0. You might have a different equation. Your equation might be minus 14 plus 4 minus 10 minus 6I2. But it should be either this equation or the exact negative of this equation. You would get it to be the negative of this equation if you went a different direction than I went. But it doesn't matter. You're not incorrect. It's just different. All right. The lower, let's start right here, and I'll go in this direction. I get plus 10, 10 minus 6I2 minus 2I3 equals 0. Notice that I'm watching my subscripts, that when I'm in this part of the circuit, I use I3. When I'm in this part of the circuit, I use I2. And then I also watch my signs. Let's do the big loop. See, I'll start up here and go in this direction. I get 14 minus 4I1 plus 2I3. And that's all equal to 0. And then I also have the junction rule. And the junction rule says that incoming equal outgoing. I'll just pick this junction. That would be I1 plus I3 equals to I2. All right, so now I want to solve these for the currents. And notice that I have two equations in every, or two unknowns in every equation, except for this one. And so I'm going to pick one equation and solve it for one variable, and then plug it into another equation. Let's see, how would I do this? What do I want to do? Oh goodness, this is not easy actually. Well, you know what we can do? We can solve this equation for I1 and put it in here. Say I1 is equal to something, something in terms of I3. And then we can solve this equation for what? I2 and put it right here and have something, something in terms of I3. And then this whole equation will be all in terms of I3. So given that attack, let's take this equation and solve it for I1. That's I1 equals 2I3 plus 14 divided by 4. So that's I3 over 2 plus 7 over 2. All right. Then I can take what I say this equation and we'll solve it for I2. That's going to be 10 minus 2I3 over 6. That's going to be 5 over 3 minus 1 over 3, or minus I3 over 3 rather. And then we plug both of those into the junction equation. And I'm going to get I1, which is I3 over 2, plus 7 over 2, plus I2, or rather plus I3 rather, equals to I2, which is 5/3 minus I3 over 3. And then we can solve that equation for, I3. All right? So that's how you would attack the system of equations. Let's see, I'll help you out. We'll just do this one. To simplify this, I can multiply through by what value on both sides? 6. I multiply through, that's the common factor, or 2 times 3 is 6. So I get 3I3 plus 21 plus 6I3 equals 10 minus 2I3. And then that makes our math a lot easier, just gets rid of those fractions. Which, if you're used to using your calculator, often on these, you'll get these fractions. It's easier just to keep them as fractions for this reason. And so I get 11I3 equals 10 minus 21 equals a negative 11. So I3 equals negative 1 amp. The negative means that I3 equals 1 amp. And notice that I chose I3 to the left, so it's actually 1 amp to the right. The first one is the hardest, but once you get the first one, I can plug in I3 here. That's going to equal to 4 amps. 1 over 2. Excuse me. Don't write that down. It's actually going to be negative 1 over 2 plus 7 over 2. That's 6 over 2, which is 3 amps. Notice what I've done here. I got I3 equals negative 1. I have to keep that negative until the very end. So when I plug that negative in up here to find I1, I get negative 1 over 2 plus 7 over 2. Please make note of that, because if you don't keep that negative until the end, you will get it wrong, like you'll do the math wrong. And while I'm not terribly concerned about, I am concerned actually about your system of equations, but I'm more concerned that you get the sign conventions right. But I want you to be able to solve a system of 3 equations. That's something you need to know how to do moving on into your upper level courses if you don't yet. And if you do now, that's fine. You get an easy question. Yes.
So I3 is supposed to be positive, right?
I3 came out negative, but a negative current, that doesn't really mean anything. So we just switched the direction of the current. Whatever we chose, we had chosen it to the left. It's actually to the right.
Well, we have to change I1 and I2 as well.
Well, I1 comes out positive, so 3 amps. We chose the direction of I1 correctly. So I1 is 3 amps to the left, which is the direction that we chose. And then I2 is going to be 5/3 minus negative 1 over 3. So that's 2 amps. So I2 is going to be 2 amps to the right, because it comes out positive.
Just because we get I3, doesn't mean the other two are wrong.
No, just because we get I3 negative doesn't mean the other two are wrong. But you have to keep your values as positive or negative until the very, very end. And then when you get to the end, you say, oh, I3 was negative, that means I chose the direction incorrectly. Not a big deal, you just switch the direction. That's what that negative means. You shall have a question very similar to this on the test of different numbers, but you will have to solve a system of 3 equations in order to get the answer. It takes practice, okay? And it takes sort of being fastidious about getting all the subscripts and stuff right. You'll have to choose direction. But it doesn't matter the direction you choose. Any direction you want. Doesn't really matter. Okay? Y'all have a great weekend. Hey, listen, I know on Friday some of you are coming in 5 minutes late because you're missing what I do on the weekend. You don't want to tell me. The next time, I'm going to pick you out. But hey, what are you doing this weekend? Okay? Y'all have a good night. So please come on time.